Hi. Uh, so, can you see my screen? Got it. How about it? Okay, I think it's okay. Mhm. Hi. Hello. Got it. Yeah, thanks for letting me know.
It's raining outside.
Yeah, it sort of feels chilly.
It's good to have some water.
Mhm. Hmm? Next spring, I think, provided a Bible job. So it's conditional.
Let's see.
Hmm. Yeah, yeah, sure. So may I start? Okay, then let me start.
Sure. So thanks for coming, everyone. So we have speaker today, Genhee Cho from UConn. He will talk about his PhD program.
Yeah, thanks for the introduction. So today I'd like to talk about the equivalence of invariant metrics in hyperbolic complex geometry. So please do not hesitate to interrupt or ask any question during the talk, if any. So let us start with what we are all familiar with. So we saw this lemma from complex analysis. So this D stands for the unit disk in C1. So consider any holomorphic function from unit disk to itself. Then we know the following inequality, and there is also local inequality as well. So if you remember the proof, so proof is based on the maximum principle in the case of the Schwarz lemma, and then we just put the Möbius transform to get this complicated inequality. So let us think about the geometric interpretation of this rather than just the analytic proof. So as a matter of fact, the unit disk in C1 is special in the sense that this is a hyperbolic surface, right? So there is a geodesic distance, so-called the Poincare-distance of the unit disk, and the local function gamma d here. So once we put this in these two tensor, this gives the Poincare metric of the Gaussian curvature equal to -4, and the corresponding geodesic distance has this form exactly. So rather than this complicated inequality, so let us use the Poincare distance to describe the same lemma. Then you can see the meaning more precisely. So for any arbitrarily holomorphic function from unit disk to itself, so there is some contraction property. or time to time some reference says this is a distance decreasing property, and also that contraction holds in the local comparison. So Schwarzschild lemma actually means that the Poincare distance and the Poincare metric possess the contraction property by holomorphic function. So from here one can see some very interesting consequence. So now let us consider the automorphism. So always automorphism I mentioned means the f and the inverse map is holomorphic. Then from the inverse map, we can also flip this inequality in the case of the automorphism. So consequently, automorphism implies that this inequality must be equality. In other words, arbitrary automorphism must be isometry with respect to the Poincare metric. So this interesting observation suggests the definition of the invariant matrix. So the definition is for the arbitrarily complex manifold. And I think most of us are not familiar with the Finsler metric, but we'll see the concrete examples in a second. So F means either Finsler metric or Hermitian metric. Then we say F is invariant if for arbitrary automorphism, so the pullback gives the same thing. So in other words, any automorphism becomes the isometric with respect to that either Finsler or Hermitian metric. And there are four classical well-known invariant metrics. Number one, the Carathéodory metric. Two, Kobayashi metric, and the complete KE metric or complete Kähler-Einstein metric of negative scalar curvature, and the Bergman metric. And we'll see those definitions in later slides. And in particular, the later two metrics are Kähler, so we'll also give some basic remind what was the Kähler metric. So let us start with the Carathéodory metric. So we start from the arbitrarily complex manifold, and we just take one point from the space and just pick just a one vector. So you see that we just take the one vector field. It can be either local or global, it doesn't matter. So in that sense, such a metric is usually called by the Finsler metric. So it does not allow to have the quadratic realization, so because it takes just a single vector. So gamma m is defined as a supremum of this quantity. This norm is just a Euclidean norm. And we just take the holomorphic function f from m to d. So you can see that from arbitrarily complex manifold, we just map the given point to the origin and take the natural differential at that point p, and also just send that vector v to here and just measure the natural length and just take the supremum among such choices of all holomorphic functions. So from this definition, you can see that this definition requires the bounded holomorphic functions. So for example, let us take M to be just a Euclidean space, Cn. Then from the Liouville theorem, we know that there's no bounded non-constant harmonic function. So such f must be always constant. So df must be always 0. So in other words, Carathéodory metric can be essentially vanish everywhere. And what if we take just a unit disk? Then this gamma d, one can show that this gamma d exactly becomes this guy. And this is a local description of the Schwarzschild lemma. In other words, Carathéodory metric is nothing but the Poincare metric. And this metric has been investigated for several decades, and there are so important open questions, even though those are open from the 1960s. So one of the natural open question is the following. So consider the simply connected, so topologically most simplest version, complete non-compact Kähler manifold with the negative Riemannian sectional curvature range from dimension 2. So people want to show that the Carathéodory metric is not identically 0. So what if we consider n equals to 1? Then we know the uniformization theorem. So such m must be always nothing but biholomorphic to the unit disk, so that this is nothing but the Poincare metric. So it is reasonable to believe that for the higher dimension, at least the Carathéodory metric is not vanish everywhere. So one can weaken this open problem just a bit. So we just put the same assumptions over here, but just require that there exists a non-constant bounded holomorphic function. And even though this is true, it does not mean that gamma m is actually induces the topological distance. So this is some weakened condition than the previous problem. And there is some progress by John Bland in Toronto University in 1885. But this sufficient condition, even though it gives the existence such a function, but this condition is quite difficult to check with the concrete classes of complex manifold. So other than that, there's no further progress as far as I know. And if we consider more special class of the complex manifold, say, so we will also see this definition in later slides. So let omega be a bounded weakly pseudoconvex domain from dimension 3 and put the strongest assumption on the boundary. So people want to also show that this Carathéodory metric induces the topological distance because this gives the infinitesimal metric so that it can give the arc length, and then by taking the natural infimum we can also define the notion of the distance. And people want to show that that distance is actually complete. So this problem is usually called by the Carathéodory completeness, and n equals to 2 case was already solved, and this is published in Annals of Mathematics, and no other progress other than that. So as long as the definition of the Carathéodory metric was simple, but the problem is actually quite difficult. So Kobayashi actually changed the definition a bit, and what he said was, so he said the Kobayashi metric is the dualized object of the Carathéodory metric. So as we saw the definition over here, this Carathéodory metric requires the function from the manifold to the unit disk. So let's just flip the positions. So the Kobayashi metric also requires just a single vector field. So in that sense, Kobayashi metric is also the Finsler metric. And it just maps from the unit disk to the given manifold. So this manifold is also arbitrarily complex manifold. And we just require the radius capital R for the domain. And for given point P and the tangent vector V, just send the origin to P, and the natural differential just makes the sense to the just a given tangent vector for arbitrary holomorphic function, and put the infimum over here. So naively speaking, this means that so this is the maximal radius of the capital R. So we just send the maximal radius of the one-dimensional radius in this given manifold in that direction. So this is sort of the not that difficult exercise. So people can show that for the arbitrarily complex manifold, the Carathéodory metric is always less than or equal to the Kobayashi metric. So this is not that actually quite difficult. And there's some fundamental result from Lampert in Purdue University. So he showed that for arbitrarily convex domain in Cn, always Carathéodory metric is exactly coincide with the Kobayashi metric. So people might wonder that what if the converse is true? So this condition might imply that such a M must be the convex domain. And this question was also open around the 2 decades, and now we know the answer. So there is some example. So this domain is usually called by the symmetry by disk. So just take the element from the unit disk in C1, and for the first entry, just take the summation, and the second entry, just take the product. This is called by the symmetry by disk. And one can show that this domain is not biholomorphic to any convex domain, but still Carathéodory metric and Kobayashi metrics are the same. So this does not imply that it must be the convex domain. And we'll see.
Question.
Sure.
So from Lampert's theorem, so any domain that is biholomorphic to a convex domain, that these two are the same. Right?
Yep. Because Carathéodory and Kobayashi metrics are biholomorphic invariant, so this condition always implies that it is biholomorphic to a convex domain. Yeah, that's a good question. Thanks. And there are also quite important conjectures, not only differential geometry, but also algebraic geometry and even number theory. And one of the long-standing conjectures is called the length conjecture. So complex projective manifold means that this is a complex submanifold in CPN. And people want to show that the Kobayashi metric on this manifold induces a topological distance. So we are not even asking the completeness, just asking that whether or not such a Finsler metric induces a topological distance, if and only if there's some terminology in algebraic geometry. So M together with our submanifold or subvarieties are called the off-general type. This means that the canonical line bundle is big. So this terminology, I will not mention the precise definition, but this bigness is implied by the amperness in also differential geometry. And there is some important progress in 2016 by Damin and Professor Yao. So given the same complex projective manifold with the negative polar sectional curvature, then canonical line bundle must be always ample. And amperness always implies bigness. So for such a class of the complex manifold, the length conjecture is verified from this theorem. And the Kobayashi's conjecture is the considering the special class rather than just the projective manifold. So consider M, which is the projective manifold, but it is the hypersurface. Hypersurface means that locally it's written by the zero set of the holomorphic functions, but now we require the just a zero set of a polynomial. So required a certain degree for that polynomial. So people want to show that. So for this kind of the manifold, the Kobayashi metric induces a topological distance if and only if the degree has certain lower bound. And this conjecture is still open, even n equals to 2. And there's also open conjecture called Green-Griffiths conjecture, which says that so the Kobayashi metric should be well defined before this map is actually defined. What I'm saying is, in order to define this Kobayashi metric, this R must be finite. So if R becomes infinity, this means that the Kobayashi metric must be generic. So in that sense, people want to show that for any holomorphic function from C to M, this is usually called by the entire curve. So the all images belongs to certain proper algebraic submanifold or subvariety. So this conjecture is also widely open. And if we consider the just the domain case, so consider the bounded weakly pseudoconvex domain in Cn. So now we just put the smooth boundary over here instead of the analytic boundary for the Carathéodory metric case. So also people want to show the completeness issue. So still this is open from dimension 2. So there are two more invariant metrics called the Ke and Bergman metric. And I first want to review the very basic in Kähler geometry in order to understand the notion of the Kähler metric. So given arbitrarily n-dimensional complex manifold, we say the Hermitian metric is just a positive definite Hermitian inner product, as we know. And this metric varies smoothly for any point. And I think all of you already know the meaning. So very smoothly just means that sorry, there's some theory. So for any point, so we can always find the standard local basis, and this function Gij bar for any indices, this becomes the smooth function. That's the meaning. And one can take the dual basis, and then one can write down the Hermitian metric in this way as a 2 tensor, and there's a Z bar over here, but there's no Z bar, and this is just a description of the Hermitian metric. But as long as this has a complex value, one can take the real part and the also imaginary part, and one can show that once one take the real part, then this exactly becomes the Riemannian metric. So this is usually called by the induced Riemannian metric of G, and the imaginary part becomes the real differential 2 form. So up to some constant, so one can find the associated one-on form. So there's a wedge, so that this is alternating 2 form. And this imaginary number here should be exist in order to make the real form. And this is the description of the, you can see that this is actually the 2 form. And there are 2 canonical connections that one can use. So given our arbitrarily Hermitian metric, then there is a so-called a Chern connection, which requires the compatibility with the metric and also compatibility with the complex structure, whereas also Hermitian metric induces the Riemannian metric, so that we have just a Leibniz-Zeta connection, as we know. And those 2 connections exactly are the same when the metric becomes Kähler. And we say the Hermitian metric becomes Kähler if it is symplectic. In other words, the corresponding associated one-on form becomes declosed. And there are several equivalent descriptions of the metric being Kähler. And one of the nice description in differential geometry is that the Hermitian metric becomes Kähler if and only if one can find such a actually holomorphic normal coordinate for arbitrary point that Gij bar becomes the Dirac delta, and this D becomes just a 0. So you might realize that this condition is nothing but the normal coordinate in Riemannian geometry, but we require the holomorphicity over here. So this is stronger than the Riemannian normal coordinate. So in that sense, such coordinate is called by the holomorphic normal coordinate. So existence of holomorphic normal coordinate is same as to require that the Hermitian metric is being Kähler. And there are 2 examples, as I said, for the invariant metrics. So given arbitrarily complex manifold, then Kähler-Einstein metric is, from the terminology, it must be Kähler, but also requires the Einstein. In other words, it's proportional to the each tensor. And the definition of the Bergman metric requires some machinery, so let's be patient just a bit. So given arbitrarily also complex manifold, then one can consider the space of the smooth complex N0 form, so there's no Z bar over here. And one can associate a natural inner product that just put the just a complex conjugate over here and just take the wedge, then this just assume that this integration is well defined, so that we have a natural norm over here. So one can take the L2 completion of such a space, and this space becomes a separable Hilbert space. And because we are considering the complex structure, so just collect the element with the holomorphic condition. Then one can show that such H, so just assume that H is non-zero, and one can find the orthonormal basis from this space. So just wedge those orthonormal bases and make the just a series. So this guy is usually called by the Bergman corner, and this is just the NN form. So in the local description, we can always extract the local function over here, and then just take this function and just take I times dd bar of log. So this function is usually called by the Bergman metric. And from the definition, because it is defined as a symplectic form, so this metric must be Kähler from the description. And one of the canonical example is definitely the unit disk in Cn. Then we have the well-known Poincare metric, which can be written in this form. So this is associated one-on form, which is also symplectic from this description. And one can show that once one compute the Holomorphic sectional curvature, then this is constant everywhere, and that value is exactly -4 over n plus 1. And in fact, it has also constant Lich curvature. So this metric is complete Kähler-Einstein metric of negative Lich curvature, and this is also Bergman. And as a matter of fact, so the Carathéodory metric and the Kobayashi metric is exactly same with the Kobayashi metric up to the dimensional constant. So four invariant metrics that I introduced, Carathéodory, Kobayashi, and Bergman and complete K metric, those are nothing but the generalization of the Poincare metric on the unit disk. But now we consider the arbitrary complex manifold. And because now we are considering the complex manifold, there are two different notions of the curvature, which are not in the Riemannian geometry. So one is the notion of the bisectional curvature. So one can write down the curvature tensor from the Chern connection, which is nothing but the same as a Levi-Civita connection in the Kähler case. So just they put two vector fields and take so this J means the complex structure. So just put those vectors in this way and divide by each norm square. And the Holomorphic sectional curvature just put same x and y. So it just requires just a single vector field. And usually the Riemannian sectional curvature condition is stronger than the bisectional curvature. And also bisectional curvature is also strictly stronger than the Holomorphic sectional curvature. So now we are ready to understand some important theorems and conjectures in Kähler work. So let us start with the n-dimensional, complete, non-compact, simply connected Kähler manifold, and just put the non-trivial Riemannian sectional curvature range. So the upper bound is 0, and the lower bound is -1 over r to the 2 plus epsilon. So this r is the geodesic distance from some arbitrary point, and this epsilon is some positive parameter. So in that case, they show that the M is biholomorphic to just a Cn. So the reason to put this epsilon over here is the Poincare metric satisfies the decay condition, which is r to the -2. And also this upper bound is also different condition from the Poincare metric case. And the proof of this theorem is so-called the L2 estimate. And I will not talk about the technical detail in today's talk. But what they did is, by applying the L2 estimate, they construct the non-constant holomorphic function. And from that, they could construct a biholomorphism. That's the basic idea. Also, the upper bound of the Riemannian sectional curvature here is 0. So this condition is also different from the Poincare form in Cn. So now it might be natural to ask, so let us put our same assumption up to here, except for the Riemannian sectional curvature assumption. So just now require the finite range, and those upper bound and lower bound are negative numbers. So this condition is usually called by the negatively pinched Riemannian sectional curvature. So one of the toy example for this statement is consider the bore of the radius r in Cn with the Poincare metric. Then the Holomorphic sectional curvature is negative constant by -1 over r squared. And from that, one can show that Riemannian sectional curvature must be negatively pinched. So with this assumption, this condition is definitely different from this curvature range. So it might be reasonable to guess that under those assumptions, such M is biholomorphic to a bounded domain in Cn. So this is widely open. And there is some recent progress by Jean-Paul Mosen. So he constructed some simply connected but complex projective variety. So this is not, at least not the domain, such that the bisectional curvature is negatively pinched. So as I said, this condition is stronger than the bisectional curvature, and projective variety always is compact. So condition is a bit different, but this in some sense implies that the Riemannian sectional curvature cannot be weakened by the bisectional curvature. But this is not published. And one can also make the weaker conjecture that under the same assumptions, just require that there exists a non-constant bounded holomorphic function on such a Kähler manifold. And there is some important progress on considering those conjectures. So let us consider all same assumptions up to here. So say complete non-compact simply connected Kähler manifold satisfying the Riemannian sectional curvature negative pinch assumption. Then surprisingly, complete KE metric of negative Lich curvature equal to -1 and the Bergman metric, and so this is just a full name of the Kobayashi metric. So Kobayashi metric all exist first of all, and all those three invariant metrics are uniformly equivalent by the given base metric over here. And that uniform constant only depends on the curvature range and the dimension. And the way of the proof is similar. So also they use the L2 estimate to show the so-called bounded geometry. I will talk about it in the later slide. And based on this theorem, so you can see one missing invariant metric, which is the Carathéodory metric, right? So this conjecture is so reasonable that under the same assumptions, also the Carathéodory metric should be uniformly equivalent to other invariant metrics. So what I want to talk about is, let us sort of assume that all those conjectures are true. And let us see then what we can actually ask. So let's define certain natural classes of the domains in Cn, which are widely actually studied in several complex variables. So let us consider arbitrarily bounded domain in Cn. And I just put the C2 boundary in order to give the precise definition, but this condition can be weakened in several ways. But let us just put this in our talk. So omega is strictly pseudoconvex domain. Say, if there is a pluralistic harmonic, or simply say PSH, function from Cn to R, such that this omega can be realized as R is strictly less than 0, and the complex Hessian, which means complex dd bar R, on the boundary is the positive definite. So usually from this description, one can put the Riemannian metric induced from the complex Hessian. So in that sense, this boundary is usually called by the CR or Cauchy-Riemann manifold, or the certain class of the sub-Riemannian manifold. And considering the strictly pseudoconvex domain, there is a well-known conjecture which is solved recently. So consider the smoothly bounded strictly pseudoconvex domain. So let's assume that if the Bergman metric is exactly nothing but the Kähler-Einstein, and we already know the Bergman metric is always Kähler, so it just requires that the Lich curvature is just a constant by some negative constant. In that case, such a domain is biholomorphic to the 4. So n equals to 2k was solved around 2 decades ago, and the higher dimension was solved by those two mathematicians really recently. And let us just also make this condition a little bit weaker. This is called by the weakly pseudoconvex domain. So all descriptions are the same, except for this description. So the complex Hessian on the boundary, now it becomes the positive semi-definite. So it seems just a small difference, but it causes a lot of actual difference. I mean, the geometry of those domains. So one of the nice classical result of Professor M. Mok and Professor S. D. Yao is that, so a bounded domain in Cn admits a complete Kähler-Einstein metric of negative scalar curvature, if and only if such a domain must be biholomorphic to a bounded pseudoconvex domain. So here pseudoconvex domain means the weakly pseudoconvex domain. It does not need to be strictly. And in the case of the strictly pseudoconvex domain with a certain regularity, so this condition might be necessary. So in that case, one can always find the complete Kähler metric of negatively pinched Riemannian sectional curvature. So one can either combine with recent Damin and Yao's result, or one can also independently show that all 4 invariant metrics are uniformly equivalent by some constant. However, for the weakly pseudoconvex domain, this is not held anymore in several ways. especially the equivalence of invariant metric fails from dimension 3. So I also provide some well-known counter examples. So below are examples of weakly pseudo-convex domain of the so-called finite type with smooth boundaries. So one can always find the biholomorphism to make those two be the bounded domain. So this is the case that Bergman metric is not equivalent to the Kobayashi metric. And this is the case that Holorn sectional curvature of the Bergman metric can be negative infinity for some boundary point. So such phenomena does not hold.
First example, question is that in the first example, is that simply connected?
I think so. Yeah. Once one described the biholomorphism given in this paper, I think this domain is simply connected, I think. And one can also just directly show that by choosing the parameter. So this is simply connected, I think. Just take the t times the element, and as t goes to 0, that belongs to this omega. So one can show that simply connected as well. So one of my research concerning the invariant metrics is considering the bounded weakly pseudo-convex domain. So without any boundary regularity. So just denote C omega as a Carathéodory-distance induced from the Carathéodory metric, and this dke means the distance of complete Kähler-Einstein metric of Lich curvature equals to -1. Then from the Gauss-Schwarz lemma, one can always show that Carathéodory-distance is always less than equal to the distance of the complete Ke metric, and what I show is those are always different. So proof is based on Gauss-Schwarz lemma and Montel theorem in complex analysis, but I will not talk about the proof. But this theorem is interesting in two ways. One is that, so this is quite general. However, what people actually want to know is the positive lower bound of the either Carathéodory metric or Carathéodory distance. But from the Schwarz lemma technique, one can always find the upper bound. So in that sense, so people want to find the lower bound instead of the upper bound, even though it might be a bit interesting. So now let me go back to the same theorem that I mentioned. So under those known facts, so this conjecture 1 means that such a manifold, Kähler manifold, is biholomorphic to a bounded domain. And you can see that there exists a complete Kähler-Einstein metric of negative Lich curvature. And as I said, if this manifold is biholomorphic to a domain, then it must be the pseudo-convex domain by Professor Yao and Mok's result. So it might be reasonable to ask, then is it necessary such M should be biholomorphic to a strictly pseudo-convex domain? Because in that case, we can always find such a complete Kähler metric satisfying all those assumptions, first of all, and the conclusion is also true. Whereas for the weakly pseudo-convex domain, one might not be able to find such a complete Kähler metric, and the consequence is also not true. And the answer for this question is no. There's some counterexample, so-called the complex ellipsoid. So this is one of my research published last year. So just define such a domain in Cn cross Cm. So one can see that this condition just means that if one put p equals to 1, then this is nothing but the unipole for the arbitrary dimension. So, but if one consider p is strictly greater than 1, so one can show that this domain is not strictly but weakly pseudo-convex domain. So my first result is that for arbitrary dimension, one can always find the complete Kähler metric with negatively pinched Holorn sectional curvature, not Riemannian sectional curvature. But still, those 4 invariant metrics and with this base metrics are uniformly equivalent by some constant. And if one consider the dimension 2, so if one just put n and m equals to 1, so that this is just a 2-dimensional domain. So in that case, one can already show that Bergman metric is not equal to the complete Kähler-Einstein metric up to some constant if and only if that is not Bohr. So except for the Bohr, Bergman metric is not proportional to the Kähler-Einstein metric. And in fact, this is also related to some conjecture. As I said, Chang's conjecture says that for the strictly pseudo-convex domain, if the Bergman metric is coincide with the Einstein metric, then it must be biholomorphic to Bohr. But this is the case of the strictly pseudo-convex domain. However, over here, even though this is not the strictly pseudo-convex domain, still Chang's conjecture can be extended to the weakly pseudo-convex domain. So it might be reasonable to ask, what if the Chang's conjecture is true for the weakly pseudo-convex? That is also reasonable to ask. And still the question is unknown. So one can also make the weaker assumption on the Holorn sectional curvature instead of the Riemannian sectional curvature. So in that case, one can see the assumptions are changed a bit. So first of all, now there's no non-compactness, and also simply connectedness is also removed in this assumption. So, but still, one can find the complete Kähler-Einstein metric of the Lich curvature equals to -1, and also Kobayashi metric, and the base metrics are all equivalent. So there are two invariant metrics in this consequence. So one can say that simply connectedness and non-compactness are not necessary here when one just require the Holorn sectional curvature. But one can say that the Bergman metric is missing in the consequence. So from this theorem, so there's one useful observation. So what if one just consider the Bergman metric over here? And let's just assume that Bergman metric is complete and the Holorn sectional curvature is negatively pinched. So now let us just assume it. So in that case, from this theorem, we can see that the Bergman metric should be also equivalent with the complete Kähler-Einstein metric and also Kobayashi metric. So, and on the other hand, so the Holorn sectional curvature condition is weaker than the bisectional curvature, and also bisectional curvature is weaker than the Riemannian sectional curvature. So one might even ask, like the one natural question is there a complete Kähler manifold? So whose Holorn sectional curvature is negatively pinched, but the bisectional curvature does not have a sign? And if one asks this question, then one of the somehow trivial answer is just the D cross D. So if one considers the product manifold, then the bisectional curvature from the definition, it must hit the 0 for the curvature. And homogeneous domain is not interesting in the sense that the Bergman metric is always equal to the Einstein, and one can always show that this consequence is whole. So let's just accept those trivial cases and ask the same question. And one can find the also such interesting actually class of the manifold. The answer is yes. So the symmetry by disk. So if I remind you, so symmetry by disk was the first example, which is not biholomorphic to the convex domain, but still Carathéodory and Kobayashi metrics are exactly the same. So this is also the example that, which is my next result. So consider the symmetry by disk, which is weakly pseudoconvex domain. This is also not strictly. So this is usually called by the C-linear convex domain. So I worked this with Professor Yan Yan in Syracuse University. So one can show that the Holorn sectional curvature of the Bergman metric is negatively pinched, but the Holorn bisectional curvature is positive somewhere. So this theorem is just based on the direct computation, but the computation is quite interesting. So the way to show this, so as we introduced, the Bergman metric is the invariant metric. In other words, all automorphisms are isometric. So let us consider the natural surjection from D cross D to G2. So just send Z1, Z2 to here. So this is just some natural surjective map. And obviously this is holomorphic. And then then one can show that in terms of this coordinate, one can show that the Bergman corner can be explicitly written in this coordinate as follows. And then now take some benefit of the description, the automorphism of this symmetry by this, then one can show that it just suffices to compute all curvature quantities over here, x, 0, and x is real valued between 0 and strictly less than 1. So one can just reduce all computation by using the invariance property of the Bergman metric, and one can show this from the direct computation. And this is indeed the first example, except for the trivial classes. But when one proceeds the practical computation, I mean numerical computation of all those curvature quantities, some practical aspect must be considered. So one can just mimic the computation as long as they know the explicit description of the Bergman corner. But from dimension 3, it is really difficult to proceed the numerical computation to know the range of even the Holorn sectional curvature, even though we know all explicit descriptions, but numerical computation even requires the supercomputer. And for when I use the supercomputer Yukon, so from dimension 3, it usually requires more than 40 hours to just know the answer. So now let us consider the same statement. So even though I state in this way, so as a consequence, the complete KE metric and Kobayashi metrics are equivalent with the base metric. And the basic technique is so-called bounded geometry, and there's a notion of the quasi-bounded geometry, which is weaker than the bounded geometry. And there's some long statement of what this is, but let me just give some precise and equivalent description of the quasi-bounded geometry. So given complete Kähler manifold, then we say the manifold has a quasi-bounded geometry if for any non-negative integer, then one can find the corresponding positive constant such that the qth covariant derivative of the curvature tensor is bounded by this constant for each q. So in that case, we say such a manifold has a quasi-bounded geometry. And the basic technique of this theorem is that by using the Holorn sectional curvature condition, by using the Kähler-Lisch law and using the Monge-Ampere equation, one can find the quasi-bounded geometry. That's what they did in this paper. So there is also one natural question. So let us assume that we have an explicit formula of the Bergman corner. So at least numerically, we can compute our curvature quantities. But as I said, for the practical aspect, it's really annoying to get all those values. So let us find another method. Instead of computing the computation of the Holorn sectional curvature, but still we can show the equivalence of three invariant metrics. Three means Bergman, Kobayashi, and complicate E metric without computing the Holorn sectional curvature, because this theorem requires the full computation of the Holorn sectional curvature. So that is what I recently was uploaded in the archive. So there's one recent paper that we established a new method to study the invariant metrics on weakly pseudoconvex domain, which does not require the complete computation of the Holorn sectional curvature. So one can see the statement is actually quite tricky. So as I said, let us just assume that this metric is Bergman, because I'd like to know that Bergman metric is equivalent to complicate E and also Kobayashi metric. So in that case, Bergman metric must possess the quasi-bounded geometry. So now let us just assume that consequence as just an assumption. So now let us just assume that Bergman metric admits a quasi-bounded geometry. And as I said, the annoying part is the full computation of the Holorn sectional curvature. So now let us just assume the Holorn sectional curvature of the Bergman metric has some value near the boundary of the given domain with some intersection of K. And here K means the certain complex subset. And complex subset can be taken from the automorphism orbit of the given domain because Bergman metric is invariant. And this K can be co-dimension greater or equal to 1. So at least this has a co-dimension 1. And by taking the intersection, this has a co-dimension can be greater or equal to 2. So what if we start from the 3-dimensional domain? Then this just requires the 1-dimensional computation. So as a computational aspect, this has a lot of benefit to show the consequence. And from here, one can induce another complete Kähler metric with Holorn sectional curvature negatively pinched, and that metric is also uniformly equivalent with the Bergman metric, and consequently, three invariant metrics with some induced complete Kähler metric over here are all equivalent, but the benefit is over here. One do not need to compute the full Holorn sectional curvature. And this is some concrete example. So consider the 3-dimensional domain, and as I said, from the 3-dimensional weakly pseudoconvex domain, the equivalence of invariant metric usually fails. So you can see that this is an intersection of the two complex ellipsoid. So in this case, this is just a weakly pseudoconvex domain. Then this domain for arbitrarily Q and R, so this is two parameter families of the weakly pseudoconvex domain, one can verify that with the concrete Bergman corner with the global coordinate, one can show that all assumptions that I put over here are satisfied. So consequently, three invariant metrics over here are the same. And if one consider Q and R is greater or equal to 1, then this domain is convex. So from Lampert result, the Carathéodory metric is also same with the Kobayashi metric over here. And one can also actually see that the computation of the Holorn sectional curvature here is extremely unknown. And let me introduce some interesting application of the invariant metrics, because one might ask then why we need to still care about the invariant metrics. So this result is with Junqing. I think all of you already know her. So consider the CP1 minus 3 point. So this domain is like the C1 minus C minus just a 0 and 1. So you might know the little Picard theorem that so from any Holorn function from C to here, such a Holorn function must be constant. So this is established more than 100 years ago. So what we first show is the Kobayashi-Royden Kobayashi metric on this complex manifold can be written in this way. So one of the reasons that we care is from the definition of the Kobayashi metric. So one can find that there is some capital R, which is described by the by the Kobayashi metric, I mean the express description. So if the holomorphic function, I mean whose domain has a radius strictly greater than this guy, then such a function must be the constant. So from the Kobayashi metric, one can find the quantitative version of the little Picard theorem, not just saying that from C1 to here, such a function is constant, but we can find the maximal radius from the information of the Kobayashi metric. And there are so many important and interesting questions on the invariant metrics, so I'm still working on it. So that's what I prepare, and thank you for the listening.
Thank you, Kenny, for the interesting talk, and everyone for listening. I guess it's time for questions.
Okay, let me know if there are any questions.
Let's see. Maybe I ask a question. So you proved that in your first paper, you proved that the Carathéodory metric is not, it's less than the Kähler metric, not equal to. Right? You means there exists a point they are not
Yeah,
the
yeah,
same.
yeah, exactly.
Is it possible to show that on some domain that the C is strictly less than K at every point? This is motivated from the classical theorem of Luke says that C is strictly less than Bergman metric everywhere, right?
Yep, yep. Yep.
So is it possible for K also strictly less than K everywhere?
So from the proof in this paper, I think I can't, because I just used the contradiction argument. What I actually did is that from the definition of the Carathéodory metric. So from this description, even for the Carathéodory-distance, so because this is defined as a supremum among bounded holomorphic function, then one can find the so-called extremer map that realizes this supremum. That from that single function, one can always extract that function cannot realize the complete KE. But for the arbitrary point, at least my argument does not work. So it might be interesting to extend. I think that's an interesting question.
It's a natural comparison between KE and Bergman, right? So as you mentioned, the chance conjecture. So this also gives you some hint, like
Yeah.
for general weakly pseudoconvex.
Yeah. Yeah. Thanks for asking.
I also have a question on this page. But first, I want to make sure if you have more than these two are the same. Right?
Those two are the same up to the constant. So you can see that constant plays a role over here. So for the Poincare ball, because this corresponds to the Gaussian curvature equals to -4, whereas this is corresponding to the Gaussian curvature equals to -1. So because of that is also strictly less than this guy.
Right. How about the case of those symmetry bounded domain, the so-called Cardan classical domain?
So it depends on the choice of the Lich parameter over here. So as long as you require the Lich equals to -1, then this is always true. But if you change this condition, then it affects this result.
You mean if it's -1, then they are the same?
They cannot be the same. So always those two are different in this sense.
One is strictly bigger than the other.
So always Carathéodory-distance is less than equal to distance of the complete Kähler metric of Lich curvature equals to -1, and one can always find two distinct points. Then, so one can realize that this quantity for that 2 point is strictly less than this guy.
And also, you mentioned another observation at page 25, followed from the result of 1 young. So what's the reason for this observation holds true?
So I just wanted to actually see that so the Bergman metric is missing in this consequence, and still Bergman metric might be still equivalent for certain classes of the weakly pseudo-convex domain. So for example, the weakly pseudo-convex domain of the finite type, so I think still it is open question that the Riemannian sectional curvature can be negatively pinched. I think it's not true. But still, the four invariant metrics on that class of the weakly pseudo-convex domain, those are all equivalent, right? So it might be reasonable to ask, then Bergman metric might have the negatively pinched polynomial sectional curvature. But this is also unknown for the weakly pseudoconvex domain of the finite time, because the upper bound of polynomial sectional curvature is +2, not negative number.
Good question for Danny. If not, we'll definitely send him again, but we will absolutely resume next quarter. So, see you then.
Okay, thank you so much. I will stay here for a moment. Okay. Yeah. Thanks for coming. So I will send the new slide because I update a bit today.
Very nice talk. Yeah, very nice talk. Yeah, for weakly pseudoconvex domain, if Ke equal to, sorry, if Bergman is Ke, then because by disk also satisfy this condition, right? By disk.
Right.
In general, in fact, any symmetric bounded domain, Bergman is K.
Right. Bergman is Ke. So yeah. So in general, is it maybe just this case is just homogeneous? Just if you can find some other cases, Bergman is also equal to Ke, but not homogeneous. That would be surprising.
I think it might be homogeneous to me, but yeah, I don't know.
Yeah. Also, that question you mentioned, yes, you compare with Carathéodory, it also might be interesting.
Yeah.
You think the comparison between Bergman and Carathéodory is not sharp?
So for the non-zero vectors, so the inequalities are restricted from Hans result. What was the?
Even on the disk, there is up to multiple.
Yeah, up to multiple, right?
Oh, yeah. If you normalize, right. If you normalize Ricci of K to be -1, well, of course, if you normalize to be, if I remember, normalized to be -m-1, then they're for both they're exactly the same. But if you normalize to Ricci -1, is the constant sharp? I don't know. Since that's not sharp, I don't know.
Yeah, I don't know either.
Maybe it's Rita conjecture something.
Because I see your the comparison result for KE, complete KE and the Carathéodory. It's a very general result for any pseudoconvex domain.
Yeah.
You always have such a comparison.
Yeah, I think it's quite general, and I'm waiting the result more than 2 years in one genre, so it's quite nice.
How about Kobayashi? It takes time. Yeah. How about Kobayashi? Bigger than KE is known.
I think nobody actually did the comparison before between Kobayashi and I don't know.
Yeah, Kobayashi and KE is right required because you require the holomorphic sectional curvature of KE, right? You instruct lemma to normally compare Kobayashi with other metric, right? So if you know holomorphic sectional curvature of those metrics, then you can get one direction. Kobayashi will be bigger, right? There's still open problem whether K lines the metric will have negative holomorphic section.
Yep.
That definitely has negative reaching. It's not known whether it has. You know the guy, as I mentioned, the syndrome, we consider inviting his former student of Fang Yangzhen called Gabriel Khan. He's working on several things related to holomorphic sectional curvature of K-line metric and also some curvature conviction of certain weird stuff. So, but that's still open, as I know.
Yeah, it's pretty interesting. I don't even know how to make the comparison between those two. I have no idea.
You need to know. But other than Schwarzlander, I don't know neither. So
Yeah, back to the comparison of KE and the Carathéodory again. So for let's say so for strictly pseudoconvex case, this is known.
for strictly pseudoconvex. Yeah,
Up to some multiple, as you said, it's 4 of them.
Oh, strictly pseudoconvex. It's actually Gangi read the paper before by Robin Graham or maybe Diderot.
Yeah.
Studied asymptotic behavior near the boundary.
Yeah.
The interior is fine. So just near the boundary, they get the asymptotic behavior of Kobayashi is similar to Carathéodory.
Yeah.
So in that case, Kobayashi is equivalent to Carathéodory. Then these
Right.
two can be controlled by Kähler and Bergman.
Right.
The upper bound can be bound by my theorem with Yao. If the background manifold has bounded geometry, then Kobayashi metric can be bounded by the background. Kähler metric. So
Right.
In particular, the Kähler metric is has bounded geometry normal. So then the Kähler metric can dominate Kobayashi metric. What I'm saying is that the other direction.
The other opposite direction.
And also optimal constant probably.
It seems, according to what you say, for weakly pseudoconvex domain, they will never be the same, right? The KE and the Carathéodory.
Yeah. Actually, they cannot be the same. Yeah.
Yeah, the Gangi's first theorem cannot be the same.
Cannot be the same, right? Very general. Yeah.
There are